Next speaker is Professor Alberto Gago. He did this PhD from the University of Sao Paulo in Brazil. And at present, he is the professor in the Science Department of University of Católica, Peru. And he is also president of the National Academy of Science, Peru. And with his leadership, the high energy physics group of that university, and they take part in this pivotal, they contributed significantly in the Minerva experimental formula from the last many years. And also, he is an active research front in the neutrino phenomenology. So he is not only the experimentalist, he is also phenomenologist. So this is complete physicist, and also his group, and he is leading a group to work in this ALICE experiment at SAR.
So, good morning, everyone. So I am very happy to be here. First of all, I want to thank for the invitation to Govinda. I am really glad to be here. It's my first time in India, and I hope you enjoy the presentation.
I'll add one more thing. I think I am thanks to him. He came almost opposite side of the globe to give you lectures. Yeah.
So before everything is fixed, I would like to say that I am going to talk about neutrino, the main background of dark matter, and also to say that I have to confess that I am more neutrino phenomenologist than experimentalist. So I have two sides on me. With that kind of change. Very good. This is laser. Laser, which one? Okay, well, let's go. The outline of the two lectures is going like this. So first, we are going to start with the neutrino historical background, which is very necessary to understand about neutrinos. Then we are going to talk about oscillations. Also, in this class, I hope that we are going to reach the main results in oscillations in 3 neutrino generations. For tomorrow, we are going beyond 3 neutrino oscillations. We are going to discuss stereo neutrino and also the absolute neutrino mass measurements. Something was talked about today indirectly about talking about dark matter, and then astrophysical neutrinos if we have time. So before talk about the history of neutrino, let's start with neutrino standard and the neutrinos and the standard model. We know that we have 3 flavors of neutrinos. We know also that there are only 3 active neutrinos when you measure the invisible width of the C boson. Also, we know that according to the standard model, the neutrinos are massless, so you don't have a Rice and singlet neutrino within the context of the standard model. Besides, we know that the neutrinos interact very weakly. We have, interact very weakly. We have the interaction through W bosons or C bosons. Also, we have this interaction, which is very weakly. We can be illustrated with this number. For instance, for one MeV neutrino, he can travel before interact 10 to 17 centimeters or 10 to 8 air diameters. You can make the calculations if you want. So basically, what we know, the neutrinos interact very weakly. Also, they are very abundant. This is not said in this transparency, but this is also true. And then let's go with the No? No. Okay, well, the history of neutrinos beginning with Pauli, when he proposed a new particle to save the incompatibility between the expected two-body neutron decay with respect to the continuum spectrum decay observed. So in order to save energy conservation, they proposed a new particle, and this is the famous letter where he wrote to send to a bunch of physicists talking about this problem. And this proposed this desperate remedy, as he mentioned. So then the past almost 30 years later, you have Fred Brains and Clyde Cowan. He performed the first reactor neutrino experiment. The idea of what they did is the same that we are doing today for the reactor neutrino experiments. Then you have this reaction, the inverse beta decay reaction. And then from this reaction, you have two particles. You have a neutron and positrons. And you are going to have two signals. One is from the positron annihilation. You have two photons from them. And also when the neutrons were captured for cadmium, which was added in this detector. So after the neutron capture, you are going to get the excitation of the nucleus, and you are going to get these gamma photons. So the coincidence between these two delay signals are going to be the signature of neutrino. So this is a project called Poltergeist, because neutrino was only a sort of ghost, because we didn't know the existence of this, if this particle proposed by Pauli really exists or not. So then in 1962, you have Lederman, Schwarz, and Steinberger, which performed the first accelerator neutrino experiment. Here, it's interesting to see what is the idea of this kind of experiment. You have a bunch of protons which hitting a beryllium target. From that, you have pions. Then you have some kind of shield. After that, you are going to get few muons and neutrinos. So the idea is, this idea is the same that you are doing with the accelerator neutrino experiments today. So what they did was the following. But from the pion, you are going to get anti-neutrino, not only muon, but anti-neutrino, and they expect if the electron neutrinos was the only type of neutrino in nature, they will expect that from this reaction, in that moment, they didn't know that muon neutrino was other stuff. They expect to have a positron at the final state, but they didn't observe that. They observe a muon. So they conclude that they have another type of neutrino. This is the muon neutrino. Then you have finally later, very later, in 2000, we have the Donut collaboration, who were the first to observe the tau neutrino. What you got here, what you have here is you have 800 GeV protons. That from this interaction with this target, you are going to get this D meson. From this D meson, from the decay of these D mesons, you are going to get taus, but you are going to get tau neutrinos. Then this going to tau neutrinos and all the hadrons that you're going to produce are going to go through the shielding. Of course, the hadrons are not going to pass through the shieldings, only the neutrinos. And you're going to get here arriving the tau neutrinos. You have a group of emulsion targets mixed with this other scintillator fiber tracking in order to track. In the emulsion target, you are going to get this kind of signature, which is the kick of the appearance of the tau after the charge current interaction of this new tau. So this was the first discovery or the confirmation of the existence of the tau neutrinos. Well, we have a lot of sources of neutrinos. I am not going to, I am not mention, I guess, all the sources, but most of them. You have solar neutrinos, which the energy of solar neutrinos is the order of MeV. We have atmospheric neutrinos, which are in the order of GeV and PeV. We have also extragalactic neutrinos, which are in the order of PeV and ExaEV. Besides, we have man-made neutrinos, sources, which are the reactor neutrinos that we are going to talk about later, with energies in the order of MeV, and we have also accelerator neutrinos with energies in the order of GeV. So let's talk about part of the history. It's very important about the solar neutrino problem. So what happened with the sun and with the sun? The sun, in principle, as you know, is a ball of gas of hydrogen, which burns hydrogens and you produce helium. And from this reaction, you produce the sun energy. This net reaction can be achieved through those kind of one through the CNO cycle, and the other option to produce this net reaction is through PP chain. In both reactions, as you can see, predicted by the way, by the John Bacall, who wrote the solar standard model, from this reaction, you can see that in some parts of this chain, for instance, you are going to get electron neutrinos. Here you have electron neutrinos, here you have electron neutrinos, here you have electron neutrinos. And then, for instance, if you want to do the exercise, if you go for some branch, for instance, you go from here, you are going to get this reaction. If you are going from here, you are going to get this net reaction. So every part that you travel from the start to the end, you are going to get this net reaction. But the point that I would like to point it out is the fact that the test of this solar standard model was the production of solar neutrinos. And this is the way that prove the solar standard model. It's going to be similar here in the CNO cycle, then you are going to get also, as catalyzers are working the protons, and you are going to get neutrinos in different parts of this CNO cycle. So let's go to the solar neutrinos, and let's go to the spectrum of solar neutrinos. The spectrum of solar neutrinos, you are going to get in this shape. For instance, you are going to get here the PP, the beryllium, the PEP neutrinos, the beryllium-7 neutrinos, the boron-8 neutrinos, the EHP neutrinos. All these neutrinos are produced along this PP chain, for instance, also in the CNO cycle. In the different parts of the PP chains, as I mentioned, you have production of neutrinos. And here that you have is just the flux versus energy of these neutrinos. Some important point to mention is that you have here gallium neutrinos, the gallium experiments, the threshold of gallium experiments, and also you are going to get the threshold for chlorine experiment, which is Homestay, and also here an upper threshold for super K as Sudbury Neutrino Observatory experiment. Well, other stuff here interesting to mention is that when this is a sum of neutrinos, this is a picture of neutrinos properly in terms of the flux of neutrinos coming from the sun, and this is more intense flux and less intense flux coming from the sun, neutrinos from the sun. Well, we have the historical experiment from Bryce Davis. Here you have Bryce Davis and John Bacall, and they perform basically what the theoretician is John Bacall, but the experimentalist is Bryce Davis. He performed an experiment in Homestay in the gold mine in Leeds, South Dakota, which is located at 1,500 meters depth in the Homestay gold mine, as I said. And this is consists in a large tank of 60 tons of perchloroethylene that's also set as tetrachloroethylene. So the basic reaction is similar, is inverse beta decay, where you have the the chlorine that capture electron neutrinos, and then this chlorine transforms in argon, and then also an argon that emits an electron. So the way that they count down neutrinos, the electron neutrinos impacting in the detectors, were removing every 60 days the argon atoms with helium gas and collecting them from the gas stream with an absorber, using carbon as an adsorber. The argon sample is placed in a proportional counter, and then this argon sample, they're decayed via electron capture, and from this decay, you are going to get since one electron is captured by the argon, you are going to have a vacancy. From this vacancy is going to be occupied by another electron, and you are going to get a photon. The energy of the photon can be transferred to the other electron, and you are going to get these called OJ electrons. So this is the way that they count the argon sample. So no, I am not going to talk about the gallium experiment because the idea is pretty much the same. So the difference is that they use, instead of chlorine, they use gallium, and they are going to get a similar reaction, and they are going to get OJ electrons, and they are going to count, in similar way. So here, what we got, which is very interesting, and is the root of the solar neutrino problem, is that if you compare, when they compare their measurements against the theoretical prediction of the solar standard model, they found this deficit. This is the so-called solar neutrino problem. So both type of experiments, the experiment based on gallium and the experiment based on chlorine, they were consistent in terms of found this solar neutrino problem or this deficit of electron neutrinos. So this experiment is very important. They only count. They did not have information about energy or direction. They only count through the electron capture. As I said, they only count neutrinos. This was the purpose of that experiment. It was radically different that Super K experiment does or did at the moment, being able to measure real-time neutrino event detection. So it means measuring the energy and the direction of the neutrinos. This Super K experiment, as displayed when I show the neutrino flux from the sun, are sensitive to the boron A neutrinos. And this is very important to notice. They identify neutrinos through this neutrino elastic scattering. When you have a solar neutrino hitting or interacting with an atomic electron, and from that you get a scattered electron, and this scattered electron neutrino. Also, this diagram is not the only one that you use in the cross-section. Also, you have this neutrino electron neutral current contribution is part of the signal. So here, the very famous Super K experiment. So you have the inner detector, you have surrounded by more than 11,000 photomultipliers. You have the outer detector. And this water sharing of detectors, the logic is going to be the same for other detectors, for instance, like ice cube. The idea is that you have a medium that when a particle, where you have the option that the particle can go faster than the velocity of light in that medium. If you have that possibility, you are going to get the like analogy of the sonic boom. This kind of radiation is called shedding of radiation. And this is also observed, for instance, in reactors. You are going to see these blue globes in reactors, which is also shedding of radiation. And what is the type of signal that you get from this kind of shedding of light? you are going to get a sort of Cherenkov rings. You are going to get some, from this radiation, you are going to form this Cherenkov ring. So this is a kind of example of the event displayed, where of course the number of photons is proportional to the electron energy. And they, for instance, they get the direction of how they know that they are coming from the sun is explained in this plot, no? Where this is the cosine theta sun is measuring the relation between the neutrino direction and the direction of the sun at that moment, at the moment of the measurement, of course. So you are going to get here are the neutrinos coming from the sun, and this is background due to natural radioactivity. So what they measured was consistent with the other experiment in the sense that they also got a deficit, a solar neutrino deficit. Well, the history ends or dissolved by this famous experiment, which is Sudbury Neutrino Observatory experiment, SNOW, which is also water Cherenkov, which is also sensitive to boron neutrinos, and some kind of details of the measurements here. You have a heavy water in this case. By the way, super K is only water, and in this case, the difference with snow is that you have very heavy water, and then you are going to get the very interesting feature of snow is that you're going to get three different types of reaction you are going to be able to measure in the same detector. One of them is pure electron neutrino charge current reaction. A pure electron neutrino charge current reaction is displayed here. You have a neutrino interacting with a deuteron, and from that you are going to get a proton, you know, another proton here, and then you are going to get this electron, and you are going to measure the Cherenkov life from the electron. Also, you are going to get the same here. Well, this is not exactly the same reaction. It is a neutral current reaction. And you are going to get also that from here an electron Cherenkov light. And finally, you are going to get the elastic scattering reaction, which is similar, which is very similar, not very similar, is similar than that reaction used from super K. That you have here, this neutrino elastic reaction. The flux is going to be composed by two components. One is coming from the pure flux of electron neutrinos, and the other one depends just in the weight of the neutral current contribution that I mentioned at the beginning. So this is the famous result from the Sudbury Neutrino Observatory. You have here this few mu tau. You should read as the addition of few mu, the flux of few mu plus flux plus the flux of few tau. The addition of both are going to give you the few mu tau. And in this axis, you are going to get the electron flux, the fusion, the electron neutrino flux. And the bands represent the different measurements from, for instance, neutral current, for charge current, and for elastic scattering. The intersection of the three are going to give you the base point of these fluxes, so the flux mu tau or the flux electron neutrino flux. Then, if you remember, the problem was that you observe a deficit on electron neutrino flux. However, with this measurement, you observe if you measure this flux with this flux are going to give you the total number of electron neutrino flux expected without any strange effect. So it was also can be seen only using neutral current, neutral current. You are going to see that the flux in neutral current, which is equivalent for all types of neutrino, divided by the flux or electron neutrino expected by the solar standard model is going to be consistent with 1. So why is important the result of SNOW? Because through SNOW, it was confirmed that the problem with the solar neutrinos was not the solar standard model, was a particle physics problem. So it was very interesting from that point of view. In fact, R. McDonald received the Nobel Prize for that. So let's go now with atmospheric neutrinos. You have seen something before in another class. Well, first of all, we have isotropic flux from cosmic rays. And then from this isotropic flux from cosmic rays, you have in the upper atmosphere, the cosmic ray can impact with protons or helium or other air nucleus. So from this impact, you are going to get pions and kaons as well. And from the pions, you are going to get muons and muon neutrinos. And from the muon decay, you are going to get electron neutrinos. So this is, you have to pay attention on that because we are going to see what happened with that ratio. So besides, we have here some calculation of this neutrino flux calculated for different authors, which is important to say that the atmospheric neutrino flux is rather uncertain. In fact, that uncertainty can be from 10 to 30%. The dependence of these uncertainties are interesting because, well, one is we don't know exactly the primary composition of the cosmic rays. Also, we don't know exactly the dronic interaction of cosmic rays with nucleons at that energy, solar activity, atmosphere modeling, and geomagnetic field effects. So, well, what happened with that? As I mentioned, you have to pay attention to this relation between electron neutrinos and muon neutrinos. And this relation is going to be proportional to 2, is expected to be proportional to 2, but this is not exactly, and this is displayed here. You are going to see that for higher energies, this is going to be distorted from 2. This is because they are higher muons that reach the ground before decaying. So in principle, for that reason, you are going to get this deviation from 2. Well, the important to use this ratio is that in somehow we are eliminating uncertainties in these fluxes, in the calculations of the neutrino fluxes. And then what happened with that kind of atmospheric neutrino experiments? They measure this double ratio, not only the ratio, but double ratio. This double ratio is muon-like respect to electron-like neutrinos in data, respect to the muon-like, respect to electron-like in Monte Carlo. If from this double ratio, they observe, well, in principle, you have these most modern experiments that were inconsistent with 1. You expect it to be 1 here. And this experiment has larger uncertainties and are consistent with 1, but also with other experiments, but they have very large uncertainties. So in principle, this is the best measurement from Super K, and then observe also in the atmospheric sector a problem in the terms that we have a deficit. So you have both problems. The other problem, you have already known the answer. This was a problem with neutrinos, they changed. And then, which is interesting to mention, is which are the neutrino interactions, the kind of neutrino interactions that are going to suffer the atmospheric neutrinos. There are 2 types of cross-section that you have to take into account. One is the quasi-elastic scattering, which is here, resonant production, and deep inelastic scattering. Sorry. If you are going to make difference between of them, besides the final states, is that the dominance of per each cross section depends on in energy. So here you are going to see, let's see, should be up here. Okay, you are going to see the cross sections. Here you have the quasi-elastic cross section. You have the resonance, and you have the deep inelastic cross-section. So as long as you are going to higher energy, you are going to different type of dominance of different type of cross-section. Also, here I am displaying the electron shower, the electron signal from atmospheric neutrinos, which is rather fuzzy due to this kind of showers that the electron produce. And the muon signal, which is a very well-defined ring. So this type of signature is well different between electron neutrinos and muon neutrinos. Well, let's go to interesting results, or the amazing results, is that the well-known Super K neutrino oscillation revolution could take place in 1998, where you have, well, let's go here. You have here this variable, cosine theta c, zenith angle. Theta c is referred to the zenith angle, and the zenith angle is referred with this axis, and you have the direction for this neutrino. So for a given neutrino, for instance, and you have to interpret here one cosine theta c1 is neutrinos coming from above, and -1 is neutrinos coming from below. Basically, this is the idea. And then also other stuff to mention is that there are two types of events: fully contained and partially contained. And fully contained is where there is no heat in the outer detector, and partially contained was they have some heat in the outer detector. So let's to see the results. This is the electron light results, and this is the expected Monte Carlo expected without oscillation. This is the data, so it's consistent without oscillation. Also, it is multi-GeV electron-like. And here is the problem, for instance, here, that we have there is a deficit in the mu neutrinos respect to the expected value for Monte Carlo. So this deficit is the so-called Super K neutrino oscillation revolution, because this was explained for some physical phenomena called neutrino oscillation. So we are going to talk a little bit about that. So this, I am not going to talk this detail because we are going to see later in the theory about what is neutrino oscillation. So this is interesting to mention that at the moment that you have both data from solar neutrino and from atmospheric neutrino, you didn't know exactly which was the mechanism behind. You expect that you have some physical mechanism that change the nature of neutrinos. I mean, transform the neutrino from one flavor to another one, but you don't know what is the mechanism behind. So in fact, at that moment, there were very competitive theories trying to explain that, and they were able to explain, but at some point when the more data were released, many of these theories were excluded. For instance, I am mentioned here non-standard interaction, or a violation of the equivalent principle, or also the coherent effects. All these theories were at some point they explain the evidence, but as the data grows, they were excluded. And it's very interesting that when neutrino happens, the Occam razor, where the simplest explanation is the usual right one, because at the end that you discover that the oscillation was for very simple mechanisms induced by non-zero neutrino mass. So let's go with neutrino oscillation. Neutrino oscillation, you are I suppose, familiarized with that. It's the process when you have started with some kind of flavor of neutrino, and then when the neutrino travels, it's going to change to another flavor, and it can change to different flavors. So this oscillation, as I said, are explained now at least at first order by induced by mass. Is suggested that somehow by Pontecorvo, inspired in the neutral count mesons oscillation. So at the beginning, the idea of Pontecorvo was the transition between neutrinos and antineutrinos, but the idea of oscillation is the same. The idea of oscillation is the same, only you have here, you have flavor eigenstate and you have mass eigenstates in the case of neutrinos, which are not aligned. And this is the reason that you have a mixing matrix. And then when you evolve this equation, we are not going to discuss that. You can revise if you do not know. It's very simple. And you are going to get a sort of disappearance probability and appearance probability. From here, if you are not already familiarized with that, you have to get the following parameters. So this is the oscillation amplitude, which is very important, the parameter from nature. And the other one is the interference phase, which is given by the square mass difference. So, of course, you are going to have a sort of oscillation wavelength, and the experimental parameter is the source detector distance, and the neutrino energy involved here. So here is the appearance probability, or the transition probability when you have you are changing flavor, and this is the survival probability, also called that like that. So basically, all the physics that we are going to discuss are going to be discussed around these cases. I mean, of course, this is a simplification because we have not only 2 neutrinos, we have 3 neutrinos. So in principle, oh, by the way, this is very interesting. If you check or think about what happened with neutrinos, at the end is a double slit interferometer. Well, you can, 3 slits, if you consider the 3 eigenstate masses, where you have these kinds of interferometry with the difference in path length is the difference in phase, it's the interference in phase that you are going to get. So here we go with 3 flavor neutrino oscillation. And then these pieces are very important to understand the results. You are going to have different sectors. You are going to be able to decompose the mixing matrix, 3 times 3 mixing matrix in different sectors. One is going to be the 2-3 sector that can be studied through long baseline experiments and atmospheric. Other one is this part of the matrix, which is 1-1-3 and S13 and delta phase. The delta phase is the CP phase. And the final sector is this one, is the theta-1-2, which is related with delta m squared to 1, and this is related with delta m squared 3-1. Also important, what we don't know now, or what we know barely known in neutrino physics. One is the mass hierarchy. What is the mass hierarchy? The mass hierarchy is the following. We have 3 types of eigenstate mass possibilities. One is nu1, nu2, and nu3. In principle, we know that nu2 is higher than nu1. I can explain you later if you want. And one possibility is that nu3 was the higher mass eigenstate, or the other possibility is that nu3 was the lowest mass eigenstate. We don't know what is the correct hierarchy. We only know that 2 is greater than 1, but we don't know if nu3 is the lowest or nu3 is the highest mass scale. So this is a problem that many experiments are trying to solve. Also, we have very large uncertainties in this variable, but a very important variable is the delta CP violation phase. If basically, how do you extract the delta CP violation phase is subtracting probability of neutrinos, of the transition between neutrinos, minus the probability transition between antineutrinos. If you make the calculations, you are going to see that this delta PCP, I am going to call like that, is proportional to sine delta. So si delta is not equal to MP, so you are going to get different probabilities for neutrinos and antineutrinos, and you are going to get delta CP different from 0, no? Or P, or multiple integer multiples of pi. So other important phenomena that you have to know when you want to learn about neutrinos is the neutrino oscillation in matter. What happens is that when neutrino propagating in matter suffers some kind of coherent forward elastic, this is a very important point, scattering. In this kind of scattering, there are no change for momentum or direction, there are unchanged. The only change, the neutrinos acquire some kind of phase. This can be translated in the term in the Hamiltonian. You can revise later with time all of this, but this has been translated in a sort of potential that you are going to add in the Hamiltonian. This potential are going to be dependent on the Fermi coupling constant, and is going to be dependent on the electron number density. So this effect, which I am going to, the phenomenology of this effect, are going to give you all the details you can revise, but I'm going here. For instance, if we think in order to learn the step by step in 2 generations, these are going to be a change in the amplitude, in the oscillation amplitude, and not going to be a change in the delta M square. How it's going to change? Here is half, but this is the interesting point for the mixing angle in matter. The mixing angle in matter are going to have here this quantity A, which is a function of this potential matter in the denominator. And look how it's going to be this behavior. This is very interesting. Here you have the formula of the mixing angle in matter. And if you have the A is respect to delta M square is greater than 1, much greater than 1, you are going to that this sine square to theta M is going to be going to 0. So this is here. This is expressed in this plot here. Also, if you have the opposite, A respect to delta M square is much less than 1, you are going to get that this angle in matter is going to be similar to the angle in vacuum, which is here. And the case when A is equal to delta M square cosine 2 theta is that you have maximal amplitude. So in principle, what is the moral of the history, or you have to, or the message that you have to get is that the matter is an effect that are going to affect the neutrino oscillation is very important to take into account. And in fact, depending on how much matter is going to transfer your neutrinos, you are going to get different results or going to be affected or not with these matter effects. So this is very important to mention. Also, the matter effects are good to, for instance, to determine the sign of delta M square, because you have this relation here. So you are going to be sensitive with matter effects to the sign of delta M square. So let's go with reactor neutrinos. 10 minutes. Okay. Well, I am going to be fast. So, well, the nuclear reactors, in nuclear reactors, you are going to have a chain reaction. In this chain reaction, at the end, this is an example. This is an example. You are going to get some stable nucleus at the end of this is a chain of reactions. This is not only the one from here to here. Not, it's a chain. And this with this kind of reaction, you are, for instance, with zirconium and cerium, you can calculate how many neutrinos you produce per fission. And this is about 6 electron antineutrinos per fission. Well, this is very interesting because, well, with this calculation, you can intuitively understand how many antineutrinos are produced per fission. So, well, when you have the reactors, when you have commercial reactors, they are based basically in this fuel. They are using this kind of fuel, this distinct high topos as fuel. So here we have. So if you combine this fission for seconds with this neutrino spectrum, reactor neutrino spectrum, which comes from different types of sources or fuel, you are going to get the neutrino flux. This point is the inverse beta decay threshold here, this point. So in fact, that you are going to be able to measure is this part of the spectrum. So let's go more quickly. So this inverse beta decay is the same that I presented at the beginning with in the experiment, the first experiment of reactor neutrinos. And then you are going to get, if you convolute the anti-reactor neutrino flux and the cross section, you are going to get this spectrum. And also here, this is the same that I talked about only with numbers at the beginning. So we have usually these reactor antineutrino detectors are doped. The most modern reactor antineutrinos are doped with gadolinium. And with gadolinium, you are going to get a delay signal respect to the prompt signal, which comes from the annihilation of the positron. You are going to get a time of 20 microseconds. And if the capture, the neutron is captured by a proton, it's going to be 180 microseconds. So the delay signal is different between when you have gadolinium or you have protons as mechanism for capture the neutron which is the secondary signal after the pro signal, which comes from the positron annihilation with matter. So in principle, we are going to get, you can calculate this. Here is important to mention, this is important to mention, is that if you analyze how is the probability of survival electron neutrinos or anti-electron neutrinos, in different pieces, you are going to get this expression. This expression is drawn here, this complete expression, and let's analyze different parts of the expression. Let's quickly analyze that. In this part of the distance to the reactors, remember that the distance and the energy is a parameter that controls how is going to behave the probability of the important contribution of the probability. You are going to get that is going to survive this part, or this part is going to be negligible, is what I am trying to say, considering that the scale delta m squared to the solar scale and the free scale are given by these numbers. So what is interesting is that you are going to get, if you go to higher distance, the reactor and the detectors, higher distance for them, between them, you are going to get these wiggles, and these wiggles are due to the delta, this is delta m squared 32. So this wiggles is due to this this contribution from delta m squared 32, and this the oscillation wavelength that you are seeing here is due to delta m squared to 1. So with good energy resolution, which is the case of Juno, for instance, you are going to be able to solve these wiggles, but this is something interesting to know. So Kamlan was the pioneer experiment about anti-neutrino detectors, anti-neutrino reactors. And this is the medium baseline of Kamlan is about 180 kilometers. This is the effective baseline. This is a bunch of nuclear reactors illuminating the flux at some detector in some position, which is relatively in the center of the distribution of these reactors. And then here we have the Kamlan detector. We are going to have more or less 1 kiloton liquid scintillator detector. This Kamlan is no doped with gadolinium, a difference with other detectors, where we have the different part, this no scintillating part, and also with the outer detector, which you have water. Works as was mentioned before in the past lecture. This as a shielding and protected from external sources for radioactivity. So here the backgrounds somehow were mentioned before. We have geoneutrinos is one of the backgrounds. Other one is the lithium helium delay neutrino beta emitters, which come from muons, cosmic muons, or the secondaries from cosmic muons. We have fast neutrons, which fast muons, muons interacting with neutrons, which produce fast neutrons, and they which produce proton and neutrons. And this mimics, in this case, these delay neutron emitters, neutron beta emitters, and this, in this case, in the fast neutrons, you are going to get this kind of proton and neutron delay signal. The neutron is going to be the delay signal, but this signal is going to mimic the same delay coincident signals that you have to observe in the case of antineutrino reactors, antineutrino experiments that I mentioned before in the several slides before as well. Also, you have this kind of background, which is very important, which you have the reaction of carbon with alpha decays, which came from polonium. The polonium is the actor of radon, which is in the air. And the prompt signal comes from the excitation of the oxygen, and the neutron is going to give you the delay signal, mimicking the results that I said before. So let's, how about my time? How?
5 minutes.
Okay. Well, the results of Kamlan, you are going to get this oscillation wavelength. You are going to observe. Here you have the low region of neutrino oscillation parameters, and this is the spectrum. And I'm going to skip this. Well, this is the more modern neutrino reactor neutrino experiment. Here, the idea is to have a near and far detector, and the ratio between of them are going to give you a very good idea about the probability, and are going to reduce, which is very important, the systematic uncertainty. This is the novelty of this kind of reactor neutrino experiment after Camlan. Also, the novelty I'm going to skip because the ideas are going to be the same. The novelty is that they are going to use gadolinium, and it means that they are going to be able to have a delay signals in shorter time, that in the case of proton, they are going to get a signal with lengther time. The difference between signals is going to be longer. In the case of protons, the neutron is captured by proton. So let's see the results. We have here the Reno and the ICFA. And what is important here is to see that, for instance, this is the ICFA. The ICFA is a reactor neutrino experiment which has gadolinium. And you are going to get that the ICFA, for instance, measures the θ13 and also some effects in delta M squared 32. Which is interesting is that the precise measurement that you can get from θ13 from reactor neutrino experiment, from this last type of reactor neutrino experiment. Well, let's go to neutrino beam. The neutrino beam is very similar. The neutrinos produced with atmospheric neutrinos. It's very similar idea, only you have in a lab, produced in a lab, because you are going to get the same. You are going to get proton, for instance, protons hitting a target, and from the target you are going to get pions and kaons, and from the decays of the pions you are going to get muons, and from the muons we are going to get muons and neutrinos, and also from the muons neutrinos, and you're going to get a flux of neutrinos. So here's the idea, and well, when you are talking about proton power, you are talking about the number of pions produced or secondaries, and this is the total number of protons on target for proton energy. So more pions you produce when you have more proton power. This is the idea. And also when you have a higher neutrino beam, you are going to get a higher energy proton. So well, this I am going to mention this very quickly. So one important problem in terms of the uncertainty when you measure this kind of experiment and you are going to use the neutrino flux is the uncertainty is in the hadronic interaction here when the proton hitting the target. This is a very important problem in this kind of neutrino experiment, accelerated neutrino experiment. This is a discussion about that, and this is an experiment designed only to get data about that in order to restrict the models of the neutrino beam flux. Well, this is an example that you have the horns in the focusing, because there are a part that I didn't mention, but there are a part in the chain of the neutrino beam where you have horns. These horns are producing a toroidal B fields, and these fields are going to focus, depending the direction of this current, you are going to focus positive particles or negative particles. So here are examples. Also, well, very quickly, this is important. You have neutrinos on axis, which means the detector is exactly or coincides with the axis of the neutrino beam. And also you are going to have neutrinos off axis. Here is the diagram of that. And what is the advantage of on axis? The advantage of on axis is that you are going to get for a wide range of pion energy, you are going to get a narrow range of energy of neutrino. So in other words, you are going to be able, exaggerating, to have a monoenergetic neutrino energy, exaggerating, of course, the situation. So you are going to be able to measure L over E, a single value of L over E. A narrow spectrum is going to help to reduce the lower high energy state with respect to the on axis, reducing the neutral current and Taos background. Well, very quickly, we have you have Minos. Minos is a sampling calorimeter. Then you combine steel and scintillator. Is the direction is going to be detected because you are going to, in the scintillator, you are going to be these wavelength shifters in different directions, and you are going to do 3D reconstruction of the direction with these three wavelength shifter within the scintillators in order to capture light from the ionization of the particle when you go through when that scintillation of the scintillation produced that you are going to get the light scintillate, the light produced are going to catch with these wavelength shifting fibers. So here you have the topology. Let's see, in order to reduce my discussion, we have electron shower mass. The energy of neutrino is going to be characterized by an electron shower plus the muon, the energy of the muon produced. The muon is get through the range to the deposit energy and also measuring the curvature. And well, the results are here. And this is the results obtained by Minos. And very quickly, you have other, this is 1 minute. In 1 minute, we finalize this. We have a NOVA experiment. The aim to measure for NOVA is to measure nu mu E and nu mu mu. And this is an off-axis experiment. And NOVA is working like that. You have a cells like this, where these cells are filled with liquid scintillator, and you have a wavelength shifting fiber here, which is connected with IPD, with avalanche photodetector. And these kind of cells are going to be disposed in this way, horizontally and vertically. And from that, you are going to reconstruct the 3D reconstruction of the direction. And you are going to get, in NOVA experiment, you are going to get this kind of long track because NOVA is very long respect to the iron magnetized calorimeter, which is Minos. It's very long. NOVA is 60 meters. And you are going to get this kind of signals. In NOVA, you have the protons and muons, a long straight track. And this is the shorter fuzzy wider shower when you have electrons and a proton. And also when which is very important is the background of the electron signal, which comes from the pi zero decay, which have this signature with these two photons produced from the decay of pi zero. So this is the last slide. You have the NOVA experiment main results. They have measured the delta CP. Here is the delta CP. T2K is also other experiment similar. They have measured as well delta CP, but and now there are very large uncertainties, and also they are inconsistent in between the results. So nothing is said. So now finalize with that slide is we are in the area of precision of neutrino experiment. This is the precision that we have for different uncertainties. And of course, we still do not know well delta CP evaluation and delta M squared, the sign of delta M squared 3.1 or 3.2. Thank you.
Thank you. Thanks for an extensive overview of this neutrino experimental results. Yeah, so very short, 1 or 2 questions.
So my question is, what about the individual lepton charge conservation?
Sorry, could you repeat the question? Sorry.
Lepton charge conservation.
Lepton?
In this neutrino oscillation, lepton charge conservation is there or not?
In neutrino oscillation, within the process of neutrino oscillation? No, in principle, not. No, only you have neutrino oscillation, but there is no lepton charge emission within the process. This is your question, no? The interaction, by the way, also, the neutrino, when the neutrino interacts, the way that you capture the neutrino is through the lepton charge, which is different than the process of the neutrino oscillation, which is a process due to the interference between the neutrino mass against state. When they travel, they interference and they get the interference phase. there is no radiation of an extra lepton charge. But when you interact, when in the interaction, there are of course final states of lepton charge, but this is not during the oscillation process. This is a separate stuff. So when you propagate, you can consider that you are propagating like neutrino mass eigenstate, and when you interact, you are interacting like electron neutrino or mu neutrino. Is it more clear now?
So my question is regarding the delta CP phase. Yeah. So what are the current uncertainties on it, and what would a non-zero delta CP phase imply?
What is the current uncertainties?
You're right. And what would a non-zero delta CP phase imply?
What is the second question?
What would a non-zero delta CP phase imply?
Okay. Well, this is the current uncertainty, but as I said, there are a tension between both. So in other words, we don't know. No, this is the final answer. We don't know. Even this uncertainty is related, measuring all the data, but actually we don't know well, because this kind of the two experiments that measure directly delta CP are no anti-2K, as I mentioned. So they know, we don't know exactly. No. So your second question is very interesting, because in principle we have matter-antimatter asymmetry, and it's expected that there will be some mechanisms if you have Majorana neutrinos that you need the delta CP phase. With this delta CP phase, you are going to be able to explain the baryogenesis. No? I mean the baryon asymmetry, the baryon matter asymmetry. So to lead to the decay of Majorana neutrinos. It's a rather complicated process, but this is the idea. So this is, for that reason, is a major goal for the experiment to measure that, because has a experimental implication. In fact, if you have in the quark sector, you have also delta CP phase, but this is not enough to explain matter-antimatter asymmetry in the universe. So for that reason, there is a hope to measure some kind of delta CP that can adjust with the theories present in order to explain that. Thank you for the question.
Okay, thanks. No, I think we have to stop here.